Okay, so question for you guys. How did yesterday go without me being here? How did the video lesson in advance work? Did that were you able to follow it? Anybody else? Yes. Would you like to go over that last question to start? Okay. So you're talking this guy right here?
Yeah.
Okay. Okay, well, why don't I take this one from the top then? The basic concept from yesterday, just a quick recap, is that Newton's third law, you've probably heard it in some capacity. Every action has a reaction force. It doesn't actually change any of the math we do, like there's not like a new formula. The key though is often in solving like tension problems. When there's like a rope between two items, the tension pulling on the snowboarder, or the snowmobile, is the same tension that's pulling on the sled. So that's kind of where Newton's third law comes in. This guy right here is being pulled up by like an applied force, but he's also being pulled downwards by tension, whereas this guy right here is being pulled downwards by like gravity, but he's being pulled upwards by tension. This tension here is the same. Does that concept make sense? Let me try the problem then. First thing we have to do is find acceleration as they go up the hill. The best way of doing this is to treat them just as like one object. So all of these guys together, what would their mass have been? 1050? I think I did this part on the video, didn't I? Did I do this part? Should I just fast forward through that? Okay, so we would have had the applied force going this way. We would have had friction going backwards. We'd have had a downward force going backwards. After doing all of this, what did we get for acceleration? I did that in the video though, right?
I think so.
I'm pretty sure I did because I made you guys do part B by yourself, right?
I got 0.4255.
Okay, so 0.4255 ... meters per second squared. Is everyone okay if we start with that premise as our acceleration then? Oh, go grab breakfast, guys. I'll get started on the diagram.
Happy birthday, Raj.
Thanks.
Happy birthday, Raj.
Thanks.
I know. We just put them on the card.
Where are you on the right?
No, I should not.
Okay. So for solving part B, the concept for finding like tension in a rope would be don't treat this thing as like one big system. Now consider these things individually. So if you're considering the sled itself, what forces are acting on the sled? Well, this direction here, like uphill, there is tension in the rope that is pulling the sled up the hill. Make sense? But if the sled is going up the hill, going backwards, you've got friction. And there's one more force in play. Yeah, there's like a downward force also pulling the sled down the hill if we draw that like that triangle in here. So there's an FD pulling it downwards, there's an FF pulling it downwards, and there's an F tension pulling it upwards, and we're going to look for that tension. Does that make sense so far? Okay. Before I get started, I better find that FD then, because I'm going to need to know its magnitude. So to find that FD, it's going to be based on gravity, just of the sled though, not of the snowmobile, just of the sled, and the angle that goes in here would be 25 degrees. So FD would be equal to, what is it, FG times sine of 25 degrees. How do you find the force of gravity? Mass times gravity?
Yeah.
What's its mass again? 50 kilograms?
Yeah.
Okay, so 50 kilograms times 9.81 meters per second squared times the sine of 25. That's going to be what your FD is. I got 207.29.
Okay.
Any issues on that? I got 207.80. No, 29. Thank you.
I was like, I got 25.
Thank you. Good catch. 207.29. Okay. So let me make my free body diagram here. Tension is pulling this guy up the hill, but there is a downward force pulling him down at 207.29. And I told you the friction force. I said the friction force just on the sled is 200 newtons. So that guy's 200 newtons. So then we need to find the tension force. Okay. So I'm going to combine a couple of formulas here. F net is going to be equal to mass times acceleration. But my F net is also going to be equal to the tension force minus the friction force minus the downward force. Does that make sense, that idea of your total forces would be tension minus friction minus downwards? So if I combine this all together, I could say it like this. My tension minus my friction minus my downward force should be equal to mass times acceleration. Does that make sense? Let me throw in some numbers then. We don't know how much tension is in the rope, but we know friction is pulling it backwards 200 newtons. Gravity, according to that downhill force, is going to pull it backwards by this amount. The actual mass of the sled is 50 kilograms, and the acceleration of the sled we already found back in part A, which was 0.4255, etc. So then all you've got to do then is add these numbers to the other side. So your final answer should be, let me grab my calculator, 50 times by 0.4255 plus 200 plus 207.29. So I got 429 newtons. I'm thinking though we only get 2 sig digs.
Yeah.
So it's probably best to call it 4.3 times 10 to the 2 newtons.
Do you need a direction for that?
I would be okay if you said uphill. Because the tension in the rope was pulling him up the hill. You're right, like some sort of direction. I mean, that's not like an official, like it's got to be this, but...
Well, because it's not a velocity, is it?
Well, okay, but a force is still a vector. Forces still have directions because they could go this way or this way or this way. So we do need to give some sort of indication as which way the force is going. Any questions on that? Did you guys get that on your own?
Yep.
Nice, okay. One more thought then. If I asked you then to find out some forces on the snowmobiler as like, let me just write them out here, the snowmobile, his forces would be an applied force of the motor, but backwards he'd actually have 3 forces pulling him backwards. He'd have friction pulling him backwards, he'd have downward force pulling him backwards, and he'd have tension pulling him backwards. Does that make sense? Okay, this snowmobiler right here, if we were doing a free body diagram for him, he's going up the hill because he's got like the applied force of 5,300 newtons. That would be this guy. Okay, but what would be his forces pulling him backwards? Well, he would still have friction. He would also still have a downward force pulling him downward. And thirdly, he'd also have tension. What is this value though for the tension? The same as the other one. And that's Newton's third law. Okay. So the tension that is pulling the snowboard, the sled up the hill, is the exact same tension that would be trying to pull the snowmobile down the hill. That makes sense? Like the tension in the rope should be the same. One of your questions on the assignment, I'm going to ask you to find tensile strength. Do you guys know what that is? Okay. A rope then would need to be able to withstand this many newtons worth of force. Okay. Like let's say it was made out of metal chains. That probably could withstand 400 newtons worth of force. What if the rope was dental floss? It would probably snap. Does that make sense? So like certain ropes would have certain tensile strengths, and so at the very least your rope better be able to withstand this many newtons or the rope itself will snap. Does that make sense?
Yeah.
So if I'm ever asking you to find that tensile strength, you're finding tension, and it needs to be higher than that. Okay? So like the tensile strength of like an airplane cable is probably like in the thousands upon millions of newtons, right? Whereas the tensile strength in a piece of dental floss is nowhere near that high, right? Like I can snap it fairly simply. You're good? Okay. You guys have any questions? Okay, let's move on. Today's topic is friction. I'm going to introduce a new formula to you. The formula itself is not going to be hard. Probably what you've discovered in physics, though, is that the difficulty is probably not the math itself. I hope it's not the math itself. It's in keeping track of what's happening. Because like with that snowmobile example, you've got forces going up the hill, down the hill, friction, downward force, applied force, tension force, right? It's about keeping track. And this formula here, we're just going to add a new formula to our list. It's not hard, but it's just about applying it in the right situations. When we try to figure out friction, we've discovered that friction pretty much happens everywhere. There's actually even friction in outer space. It's very limited, but there is a little bit of friction out there. Basically, the only way you could have no friction is if there was a complete absence of matter. For those of you guys that took my Chem 20 class, that would be called a vacuum. And that does not make sense that you'd actually have like something existing in a vacuum. Like that's not even really theoretically possible. Okay, so there should always be friction. If you were to push a block this way right here with a applied force going this way, friction would work backwards against it, kind of like Newton's third law. As I push one direction, what is the force acting in the other direction? Does that make sense, that idea of like equal and opposite reactions? I found some diagrams online that just maybe can help illustrate why friction exists. When you have a box sitting on a surface, it may seem like it's a smooth surface, like it may seem like it's actually smooth. The truth is, though, it's not. If you were to zoom in using a magnifying glass or a microscope, really these edges are slightly jagged and slightly rough. How jagged and how rough depends on the surface. If it's like made out of wood, hopefully you can kind of envision, yeah, wood actually is a little bit jagged. But like your textbooks, the table, even though it feels smooth, there are like imperfections in terms of like what it actually looks like when you zoom in. Friction. What's up? You're like scanning for somebody.
Person I'm looking for now here.
Who are you looking for?
Jessica. Oh,
Which Jessica?
Parks.
No, she's not in this class.
Oh, then
I don't actually know where she is though. Sorry.
I don't know why I'd be looking for her.
Okay.
Friction.
Friction. Yeah. Okay. Does that concept make sense then? The smoother the surface is, the less friction there will be, obviously. Does that make sense? So like when we're doing Hot Wheels on a Hot Wheels track, it's a fairly smooth surface. There should be very little friction. If I were to run that same Hot Wheels car along like concrete, like jagged cement, would it run nearly as smoothly? I'd say no. Okay. But like at a microscopic level, this is actually what is happening. There's two main types of friction that I need you guys to know about. We don't actually calculate them any differently, but there's one type of friction called static friction. It's the friction that exists between non-moving forces. I got a picture here I found. Imagine that you were trying to push a very, very large object. So large that you can't actually move it. There is friction happening. You're pushing this way, friction is pushing back this way here, and there won't be any motion whatsoever. Okay, that's called static friction. That makes sense?
So that means like when friction and your hot force equal each other?
Exactly, yeah, that would be the exact definition of Newton's third law. Your applied force and your friction force are exactly the same as each other. Nothing is moving. Okay. The other type of friction would be kinetic friction, and normally we've been working with kinetic friction. It is where the object is moving, but there still is friction happening. This would be where like you're pushing this way here. Friction is working in a backwards direction just as much. Only the only difference here is the object itself is actually in motion though. Does that make sense? So it might not actually be bigger. It is possible actually that the applied force could be the same as the friction force, and so therefore there would be no acceleration, but the object would still be moving. How do I give an example of this? It takes a lot of effort to kind of get the object moving. Once it gets moving, you can keep it going at a constant speed.
Like what you said with the rugby.
A rugby scrum would be a good example of that, yeah. Where because they're already in motion, it's going to keep staying in motion, but it won't speed up anymore. Chances are, though, the friction force will not be as much as the applied force. Like, chances are, like, the applied force will be way more than friction at this point.
I thought when they were the same.
What was that?
I thought when they were the same, they didn't go.
Okay, but what if it's already in motion? So what happens if it's already moving and then you have equal forces? So like this object is already traveling and then you have equal forces on both sides of it. It would actually keep going in motion. It wouldn't speed up.
So it's like this friction like bigger.
Well, like imagine that this arrow here, the applied force was 10 newtons and the friction force was 10 newtons. This box here could be moving still. It just won't be accelerating. The formula is F net equals ma. If these two things are equal to each other, it means you have no acceleration. But acceleration is different than velocity. You still could be in motion. Maybe a good example of that would be like a hockey player moving on the ice. The hockey player is moving on the ice and he gets hit by two hockey players with like body checks, opposite directions here. He would still keep moving forward because those forces will cancel each other out, but his motion will still continue in the same direction. Does that make sense? Okay, I found a graph that hopefully kind of illustrates what's happening here. If you were to graph the force required to move a box compared to how much friction there would be, as you apply more force, there's going to be more friction pushing back up until a certain point. So this is like me straining. I'm pushing harder and harder and harder against this really big rock until all of a sudden this point right here. What happened at this point right here? I finally got it to start moving. And so now that it started to move, now the static friction is broken, and now we actually have kinetic friction happening here. And so now I might not need quite as much force to keep moving, and now if I drop my force, I can actually keep pushing this thing, and now I'll push it using kinetic friction instead. Does this graph make sense at all? Question?
Is that kind of like if you start pushing a car?
That'd be a good example. Like, it takes a lot of effort to get it going, right? Once it gets going, though, it's actually a lot easier to move, right? Like, getting it started is the hard part. Once it's in motion, it's easier. Does that make sense? That's a great analogy or example.
So like once your applied force like is greater than your friction, then you can.
Then you actually start moving, right? And then once you start moving, typically what happens is the force needed to keep moving is less because it gets easier once it's in motion, right? Like, I mean, imagine anything that you're moving that's really difficult. The hardest part is actually getting it started. Think of like, say, a weightlifter trying to lift the weight up off the ground. One of the hardest things to do is just to get it off the ground. But once you have it in motion, your momentum, your like those sorts of other forces, keeping it going is probably not as hard. Does that make sense? Okay. Depending on then the materials that we're using, depends on what we call a coefficient of friction. Okay. Typically what happens is static friction has a higher coefficient than kinetic friction. So like if you were to have copper on copper, like two sheets of copper moving with each other, it's actually harder to get them moving from a static position than from a kinetic position. And so there's a whole bunch of like coefficients that you can either look up or find that basically like correlate to how much friction there's going to be. Does that make sense at all? So this is called a coefficient of friction, and we use them. I'm going to skip ahead in this formula here. So this is the formula we're going to use. To find how much friction force there is, you multiply this guy right here, which is like a fancy looking U. It's the Greek letter, I think it's the Greek letter nu. Anyways, this stands for your coefficient of friction. It also depends on your normal force. So to find friction, multiply this coefficient by normal force. Why normal force? Well, I want to go back a slide here, the one I skipped. Friction is because two objects are in contact with each other. Okay. Well, gravity is going to pull this object down. Okay. The heavier the object, the more that object gets pulled down. I gave the analogy when we did our lab of an air hockey table. Why does the air hockey puck move around the air hockey table so much? Well, because that air pushes it up a little bit, preventing there being that much contact, and so there's not that much friction anymore. Heavier objects have more friction. Does that make sense at all? If I'm trying to push something light, it's not hard to move. But if there's something that's heavier, it's harder to push it around. The reason why is gravity is pulling it down more. If gravity is pulling it down more, what opposes gravity? Normal force. So if gravity is pulling something down more because it's a heavier object, and normal force is pushing up more, would it not make sense that these two surfaces are pushing together tighter? Is that not going to make it harder then for the objects to slide? Does that make sense? So heavier objects are harder to slide because they have more gravitational force and therefore more normal force.
Well, then why, when you like drop a heavier object and a lighter object, they don't fall at different rates?
Okay, but that's different. That's the acceleration due to gravity. Here we're talking about an object already on the ground, right? Like if I were to give you a small rock and say push it, you could push that rock. If I gave you a very large rock with more mass, it's harder for you to push because it is being pulled down into the earth with more force, and therefore the earth is pushing back up with just as much force. So there's so much force going in this direction here that it's harder for you to slide them. Does that make sense? It doesn't affect how fast it moves though, because that's an entirely different question. Does that make sense? Okay. It's actually not hard to do for calculations. I got one more picture, then we'll do some calculations. Tires are a great example of the need for different coefficients of friction. If you are a race car driver, do you want a lot of friction? No, you want to limit that as much as possible because you've got a heavy race car. That heavy race car is pushing down into the ground. So, I mean, because it's heavy, there's going to be a lot of friction.
Oh, is that why people put weights in the back of their vehicle?
That's another example why, like in the winter, you want some weight in your vehicle. Like trucks are a good example of this. You don't want the back of your truck sliding everywhere because there's not a lot of friction. So you need to put some like sandbags in the back. I found some pictures here of like people putting chains on their tires or like big tractor tires. These guys here, they want a lot of friction so that they can actually they don't like get stuck. Does that concept make sense? Okay, let me do some examples. It's not hard calculations. Let's say you've got a 12 kilogram piece of wood placed on another piece of wood. So you've got surface 1, and then there's another piece of wood placed on top of it. And this guy right here is 12 kilograms. I want to try to figure out how much friction there is, like the coefficient of friction between them. So here's how the formula works. To find friction, you need this coefficient, which is like a fancy looking U, and you need to know how much normal force there is. This is the formula we're working with. This guy right here, it's like a U that has like a little I don't care exactly how you draw it. I'm not a writing teacher here. What's up? Good, yeah, that's what we're gonna have to do is to find this normal force here. To find this normal force, we're actually gonna have to find the force of gravity instead. Was that your question, Hannah?
Yeah.
Okay.
They
They should be the same unless for some reason this piece of wood on the bottom here is not structurally strong enough to actually hold the top piece of wood, and then it would like crash through it. But I haven't told you that that's happening. So Fg then would be 12 kilograms times 9.81. So 12 times 9.81. So I've got 117.72. So if the force of gravity is 117.72, then the normal force is also 117.72. So I'm going to tell you how much friction there was. So if there's 35 newtons and you're looking for the coefficient of friction, how do you get this little U symbol by itself? Just divide it out, yeah.
What would the units be on the coefficient?
Good question.
Divide is their coefficient.
Okay, so the coefficient itself is a number that relates how much friction two surfaces have with each other. Wood on wood compared to like copper on ice compared to like a tire on gravel. Everything's gonna have its different like coefficient value depending on like what the two surfaces are. Does that make sense? A hockey skate on ice will have a very low coefficient of friction because there's not a lot of friction between a blade and ice. But like rubber on rubber does not move very well sometimes. Like it sticks very muchly. That made sense. Okay. It will have a higher coefficient of friction. As for your answer, if this guy here is in newtons and this guy here is in newtons, coefficients of friction have no units, is the answer. So when you divide these two numbers, I got 0.297. When I round that, it's going to be 0.30. Put a little note here. There are no units for this. Sean?
Does that mean they're gonna like rub together very easily?
Well, it depends. Like now that I found 0.30, I can compare back to this chart here, for example. Copper on copper is 1.6. I mean, imagine two sheets of copper next to each other. They're probably going to grind quite a bit as you try to slide them next to each other, right? Whereas, what's kind of a lower number here? Waxed hickory skis on dry snow is 0.06. Skis on snow should not have a lot of friction. They should move quite quickly, right? So, what's the most comparable one? Maybe steel on dry steel? So that number there, like the 0.30 number that we found, really all we can do is compare it to other items, if that makes sense. Okay, so like that 0.30 on its own, it doesn't mean anything, but we can compare it to other items and see which ones are similar. Does that make sense? Most of the time, I'm either going to ask you to find the coefficient of friction, or I will give you the coefficient of friction. You need to either have it or be looking for it. Did that make sense? Okay, we'll try another one.
I know, I just saw that.
Okay, so here's an example. You are on a sled with waxed hickory runners resting on a horizontal, dry, snowy surface. Could we look up the coefficient of friction if I don't give you the coefficient of friction? So like waxed hickory runners resting on dry snow. Go back a slide. What number am I looking for?
Wait, so it tests? Do we have to remember that?
No. No, I will give you this table if you need to.
It's 0.6.
This number here. Okay. I guess the point I want to make is sometimes we can look this number up if this number exists in a table somewhere.
This sounds really funny. Wax.
So
I know.
It's waxed. Doesn't sound
okay. So looking this number up in the table gives me a coefficient of friction. What we're going to try to do is figure out the maximum mass that can be put in a 5 kilogram sled so the sled does not move but can withstand an applied force of 82 newtons. Let me draw a diagram. This is a sled. What forces are acting on the sled? Okay, well, let's say that we're trying to apply a force applied this way, then friction would need to act that way. Does that make sense? I know the applied force. The applied force is going to be 82 newtons. If this sled is not going to move, what would the friction force have to also be? Does that make sense? What other forces are acting on this thing? Okay, gravity's pulling it down, and the normal force is pushing it back up. Do we know how heavy this sled is? Okay, well, we know the sled itself is 5 kilograms, but what about the stuff that goes inside the sled? Okay, so that's actually what we're looking for. We need to figure out the mass. Yeah, this mass right here, we need to add 5 kilograms to it. Makes sense? So let me grab a formula here. The force of friction is equal to your coefficient of friction times the normal force. Can I solve for something?
Yeah, you can follow something.
Sure, solve for normal force. So force of friction would have been 82 newtons if it doesn't move. The coefficient of friction we looked up. But just so you guys know, like, if I don't give you the coefficient of friction, you have to solve for it. Otherwise, I will give you this number normally. So we could find the normal force. I got 1366. Good, yeah, and that you've got the concept then. So if this is how much normal force we need, would that not also be equal to the gravitational force? Right? Because according to Newton's third law, if the gravitational force is pulling something down, the opposite force in the other direction is pulling it back up. So if Fg is equal to 1366, and it's equal to mass times 9.81,
Do you have to include that plus 5 kilograms?
give me 1 sec, because you're right, we need to account for that in some method. When I divide by 9.81, yeah, I got 139.3. Everybody able to get that number though? Okay, now for Hannah's question then. How do we apply that 5 kilograms? Should I add on 5 more kilograms or subtract away 5 kilograms? The answer is subtract, yeah. This is how much total mass we need, but the sled itself already weighs 5 kilograms. So like the person in the sled would need to be 134 kilograms. So a 134 kilogram person plus a 5 kilogram sled, that would be the number we're looking for.
So that's the maximum weight that can fit in the
That would be the maximum amount of weight that could fit in the sled if you wanted it to not move. Actually, I think that would be the minimum amount of weight you'd have to put in the sled so that it doesn't move. Because if you put anything less in the sled, then the sled would start to move. Does that make sense? Yeah, I guess we should do sig digs though. One sig dig. Okay, so how about I change this to 5.0 because that was kind of poorly chosen by me, and then we can call it 1.3 times 10 to the 2 kilograms. Because I kind of didn't write that question very smartly, did I? One sig dig. Okay, is that fairly straightforward? The actual math, not hard. I'm probably going to say this a lot. But wrapping your head around what's happening in the problem, that's the most important part, right? Like, can you understand the free body diagram, figure out what forces are going where? So. Okay, 2 more examples, then we'll call it a day. Because 2 more? Yeah, 2 more. Okay. Another possibility is what happens if these things aren't happening on like exact angles? What happens if you push on something at a bit of like a downward angle right here? How would that affect things? It could make the friction more or less, yeah. Okay. So let me draw the free body diagram for this guy first. You've got this box, which is 67 kilograms, and you're pushing with an applied force of 700 newtons. Is all of your 700 newtons, though, going this way, like straight on? We're going to need to break this up then into like an x direction and a y direction. Does that make sense? So let's see, fx would be equal to what? 700 cosine 20? Because that would be adjacent over hypotenuse. And fy would be equal to 700 sine 20, because that would be opposite over hypotenuse. I got 657.78. The cosine. And I got 239.41. Sorry, what was the question?
Wouldn't friction just be like the FX?
Well, we're gonna have to calculate friction. We have to calculate friction.
Wouldn't friction be like the resultant triangle?
Well, friction will be based on this formula here. It's gonna be based on U, Fn. We're gonna have to find friction using the formula we just learned.
Oh, so the FY.
Okay, let me draw a diagram here of all the forces acting on this box now. Okay, here's some of the forces acting on the box. For one, there's a gravity pulling down. But there's also normal force pushing up. So far, so good? Okay. Well, you're pushing the box. Which force, though, is making the box go forward? I would say Fx is the actual force that's pushing the box that way. So I might label it as Fx is actually pushing the box forward. What is Fy doing?
Pushing it down.
Yeah, it's almost like you're kind of pushing the box slightly into the ground. What's that going to do to the friction? It's going to increase the amount of friction, right? Because you're kind of pushing slightly down, you're causing those two surfaces to come together just a little bit more, and you're going to actually increase your friction slightly. The one more force we have to account for then is that there is friction pulling us backwards. So I think these are all of the forces that are in play. Fx is what you push forward. Ff is pulling you backwards. Normal force is being opposed by Fg and by a little bit of Fy that you're pushing into the ground. Okay. Which forces do we know? We know Fx. We know this guy is the 657.7849. We know this Fy, 239.4141.
So would the normal friction just be like FY plus FG?
Good, yeah. To find this normal force, we're going to have to add Fy and Fg. So how do I find Fg then? 67 times 9.81. 657.27? Should probably put newtons after all these guys here. Okay. Unless for some reason the ground cannot hold this box anymore, the normal force plus that y force, gravity plus that y force will be your normal force. So if I want to find Fn, I just got to add this number and this number together to get Fn. So it'll be the 239, was that 4141, plus 657.27. $239.41.41. So I got 896.68. 896.68. So that's this number here. Okay, I've done a whole bunch of work. What am I supposed to be solving for anyways? Okay, so now that I've just done some random stuff, the goal is to find acceleration. Is the box going to accelerate in the up or down direction? Okay, it's accelerating in the x direction, like side by side, right? So to find your acceleration, use Newton's second law. F net equals mass times acceleration. We know the mass. We just need to find your F net. So it'll be your x force minus friction will give you mass times acceleration. How do I find friction, though? The new formula we just learned. Yeah, so to find friction, use U times Fn. So let me throw in some numbers here. We know our x force going forward was 657, 78, 48. The coefficient of friction I gave you, right? It's somewhere up there at the top, right? 0.37. We've now found the normal force to be 896.68. The mass of the box was 67 kilograms. And we're looking for acceleration. So divide by 67. So let me see if I can keep as many values here as I can. 657, 78, 48, 346 minus 0.37 times 896, 68, 41. And then divide by 67. I got 4.86. 4.86?
There's 0.37, which
0.37 was this U value, the coefficient of friction, and that was given to us up here. I got 4.86. It was 865 I got. So with sig digs, I think we only get 2 sig digs though. So I'm going to get 4.9 meters per second squared. I should probably throw a direction on there. Forward would be good. It's moving ahead, I guess. So the twist to that question there is that, I mean, there were a few other things to consider. First, we had to break our angled force up here into an x and a y direction. And then the other kicker is the normal force is not always just the opposite of gravity. I want to say that one more time. The normal force is not always just the opposite of gravity. Because in this example here, yes, gravity was pulling this thing down, but you were also pushing it slightly. And so that has to get incorporated into the normal force. Does that make sense? Okay. Sure. One more thought. Sometimes, as a way of reducing friction, if you have a really heavy object, sometimes what you like to do is lift that object slightly off the ground to then try to move it forward. Does that concept make sense? So like if you used a crowbar or some sort of crane to pull it up, even slightly off the ground, that would then reduce the normal force, which would then reduce the friction, which would make it easier to push something this way, if you can lift it just slightly up. Does that concept make sense? Sure, right? Like if you're trying to drag your table on the ground, if someone could just give it just a little bit up, the up does not actually make it go that way, right? But what the up does is it prevents it from being so much gravitational force pulling into the ground, it reduces the normal force, and that reduces the friction, which makes it easier to move. Okay, one last example. This is probably more typical of what I'll give you as like a quiz question. Just so you guys know, we're going to do a quiz on Monday. I'm probably only going to put 4 questions on it. Okay. But like the questions are questions like this, where like there's a lot of steps, right? So.
that's a lot for a section.
Well, but like keep in mind, like I'll make it out like 5 marks. So like. Yeah, like normal, right? Like it's just so you guys know, like this is probably typical of what I'll ask you, right? So let's try one last question here. There's a lot to interpret. you've got a 15 kilogram toboggan on a snowy hill, and I give you the coefficient of kinetic friction. First thing you should know then, if it's kinetic friction, this thing must be moving. Right? I'm going to give you the incline, and I'm going to tell you the length of the hill. So this is like the Hot Wheels racer. I know how long the distance of the track is. Okay. Our goal is to find length of time it's going to take this toboggan to make it all the way down the hill. And I'm going to give you two more numbers. I'm going to tell you how heavy the actual tobogganer is, and I'm going to tell you his initial velocity, because in order for him to get going down the track, he must have a little bit of velocity just to kind of get started. Heather,
Sorry.
fire away.
Okay, for like the diagram when you have to put like the weight thing, like do you add the tobogganer and the toboggan?
That would make sense, wouldn't it?
Like it's not like you have to do like one first.
No, because the toboggan and the tobogganer are right on top of each other, right? So this isn't like the string question where you have a guy connected by a rope, right? If that makes sense. So really, this 15 kilogram toboggan and the 40 kilogram tobogganer really are irrelevant. Like your total mass is actually 55 kilograms. So why don't we start there? Let's draw a diagram here. I'm gonna draw it on an incline first, though. So I've got a box, and the total mass of the box is 55 kilograms. Does that make sense that I'm just adding them together? Okay, what forces do I have in play?
Gravity,
Okay, well, gravity, like always.
downward.
Yeah, because it's at an angle, we can make a downward force. Anything else? Friction. Which way is friction going to go?
Oh, this way.
Friction will oppose the motion of the sled. So if the sled is going down the hill, in this example here, friction is going uphill. What if, though, this were the snowmobiler trying to drag something up the hill? Then friction would actually be going the other way. So, like, I can't always say that friction goes downhill or uphill. It depends on the question. It wouldn't hurt to draw in the normal force. And for the very first time, this force right here, the perpendicular force, is going to matter. We've never had to solve for this perpendicular force before, but we're going to need it now, because this perpendicular force will be the normal force.
Which one? FG,
FG should be the hypotenuse of a right angle triangle, and inside here we need an angle of 20 degrees. Okay, let's work backwards. Our goal is to find time. What are we going to need to know in order to find time? Distance, VI. What else do we need to know? Yeah, the link between dynamics and kinematics is acceleration. So our goal is going to be to find acceleration. Once we find acceleration, we can then use one of last unit's formulas. So let's start finding some of these numbers here. FG, I should be able to find that pretty easy, right? 55 kilograms times 9.81. $539.55. Let's say I want to find the FD then. How do I find the downward force? Yeah, it'll be opposite over hypotenuse. So it'll be FG times the sine of 20, which will be 539.55 sine 20. So I got 184.4.5 for FD. 184.5?
Yeah.
You got that? Okay. Sorry, 184. I'll write out a few more numbers. I got 5369. I've said this a lot before. We got to keep track of all these different forces because, I mean, there's tons of them here, right? So that's FD. While I'm at it, let's find F perpendicular. Normally I don't need to find F perpendicular, but now I do. The best way of finding it is rather than using sine, use cosine. Yeah. It would be FG cosine 20, which would be 539.55 cos 20.
I have a question.
Yeah.
About that. Can you do cosine first and then
Sure.
cosine? 'Cause that's what I do.
That'll work, so long as you get these same values.
Okay.
You could also use Pythagoras' theorem. That would also work. I'm sure you can use tan in there somehow as well. 539.55 times cosine of 20. 507? Good. I've got 0111. Okay, what's the normal force then going to be? The exact same thing, yeah. So that's good. Last force then, the only one I haven't actually solved for here, I think, is the force of friction. And to do that, I need U times Fn. I have the normal force now, though. What is the U value? Okay, now does that U value make sense? We're sliding on ice. It should be really low, right? So 0.05 times 507.0111. So I got 2535. So I would really recommend that you need to find some sort of system. I don't care how you do it, but you got to keep this organized. Okay, I can't have random numbers just like here, there, and everywhere. Like I have to be able to follow this. Okay, well now let's use Newton's second law. So your net force will be equal to, let's see, it'll be the downward force minus the friction force, and that'll be mass acceleration. Does that make sense why downward force is in front of friction force? Yeah, I mean you have some downward force, but you don't have nearly as much friction force. It's pulling you backwards, right? So you need the 184.53269 newtons minus the 2535 newtons. What was mass again? 55? 55 kilograms. Has anybody found A yet? Or am I ahead of you guys? Okay, give me 1 sec. I'll just confirm then. 2535 divided by 55. 289? Yes. 2.89. I got more numbers than that, but that should be sufficient for now. Okay, we're almost there. Some of you guys are ahead of me?
Yeah.
Okay. For the last step, by the way, just before I move on, is everyone okay with getting up to acceleration? Okay. Now we got to use the kinematics formula. We know acceleration. We know distance. Distance was 24 meters. And I gave you a velocity initial of 0.5 meters per second. The reason why I had to give you initial velocity is because it had to be kinetic friction, and you have to kind of get the toboggan going. I mean, you guys have probably been tobogganing before. You sit at the top of the hill and you sit there, right? You have to actually give yourself a nudge to get going. This is that nudge to get going. So to then solve for time, you have to use this formula. D equals VIT plus 1/2 AT squared. And it's a quadratic. Which just adds to the... Yeah, fun. That's the right word. Alright, so 24 equals 0.5 t plus 1/2 of... Should acceleration be positive or negative?
Because it still going down.
Yeah, I mean, your distance is down the hill. Your acceleration is down the hill. your velocity is down the hill. So yeah, it would make sense that this should be a positive number. Okay. 0 equals, let's see, what's 1/2 of this number? Like 1.45 t squared minus 0.5 t minus 24.
Oh, you're just telling me.
I gotta use the quadratic formula now. I used 1.4, no, not 1.47. Yeah, I should have 4 there. I got 1.44 here.
Why do you have minus 0.5?
Should be plus 0.5 t, thank you. And then minus 24 though.
Yeah.
Okay. This number right here, I actually am using 1.447, something like that, if I can. So, negative 0.5 plus or minus the square root of 0.5 squared minus 4, 1.44, negative 24, all over 2 times that 1.44. It wasn't as hard as you expected?
Yeah.
Good.
It's not as far as I expected.
I'm glad. Negative 0.5 plus the square root of 0.5 squared minus 4, 1.44, negative 24, divided by 2 times 1.44. I got a time value of 3.91. Okay. With sig digs though, let's just go back up.
1.
Again, I don't know why I keep doing this, but I apparently only get 1 sig dig. So let's call it 4 seconds.
Did you times?
Yeah, you gotta do the 2 times 1.44. Is there another value that your calculator could calculate? Is it worth calculating the negative value? It's extraneous. But I'm sure you could calculate it. It was somehow helpful.